today to have Colin McClarty to talk to us on piano arithmetic, Fermat's last theorem, and something like Hilbert's notion of contentual mathematics.
Yeah, I've got this also in English. Consider the nature and methods of ordinary finite number theory. Hilbert doesn't say finitaire or finitistic, she just says finite. It can certainly be built through number constructions by means of contentual, intuitive considerations. Contentual there translates to German inhaltlich. Hilbert's use of inhaltlich is unusual, contentual is an unusual word in English, but his idea is that these are things we know what ordinary arithmetic means, what it's about. And I want to talk about how experts emphasize the arithmetic character of Wiles's and successive proofs of Fermat's last theorem. Now, there has been a lot of progress on proofs of Fermat's last theorem, but the outline is still largely what it was with Wiles. As one put it, nobody who understands such proofs does anything but think about very small structures from start to end. Yeah, this is... The proofs, though, clearly rely on results proved in the SGA and EGA that use Grothendieck universes. Everybody involved has always known that you could eliminate the Grothendieck universes in favor of Zermelo-Frankel set theory. That's not hard at all. It's also not interesting to do, because Zermelo-Frankel set theory is already vastly disproportionate to the demands of number theory. So, so no one does that. But what I want to emphasize, what I want to talk about here, partly because people have complained that I don't talk about it enough, is that the substance of the proofs is very arithmetical. There's an impression in some circles that derive functor cohomology as this weird engine that comes in, and if you let it come in, it interferes with number theory. Well, I want to say, no, it's not a weird engine. It's there, but it's... And I want to emphasize that I think what's understood here is that the steps can be checked in any given case. And this is not banal. There are proofs in number theory where for some of the reasoning it is a little hard to relate it to concrete numbers. But I think it's typical, well, okay, I say compare the prime number theorem, another classical analytic number theory. For decades, mathematicians looked at the proofs of the prime number theorem and said, boy, I wish this was more elementary. Not because I don't believe the argument, but because I wish it was really just about numbers. The proof didn't look like it was really about numbers. And a lot of proofs in classical analytic number theory were like that. But I want to say this is typical for proofs in cohomological number theory. They do look like they're about numbers. So there's this, from a logician's point of view, it's a little bit puzzling that we're using Grothendieck universes when what we're thinking about is numbers. And why is that we're doing that? And when we say it's really about numbers, here's a step it's not hard to follow. Every Fermat triple gives an elliptic curve. If you know that a to the p plus b to the p plus c to the p, then you know that's an elliptic curve. Now, I'm being a little arch when I say it's an elliptic curve. Well, it's a polynomial defining an elliptic curve. But you can find textbooks by number theorists who say that's an elliptic curve. Because you look at the polynomial and you know it's an elliptic curve. Well, what do you have to check? You have to check that the roots are distinct. Well, sort of on display the roots are distinct, because when we require in a Fermat triple that none of them be zero. So if none of them is zero, A can't equal B and it can't equal negative B. So there's a little calculation done there, but the calculation is clear. That's a step that's very easy to follow. In Hilbert's terms, because I want to compare this to Hilbert's idea of inhaltlich number theory, contentual number theory. He says, we use letters to communicate that no matter what numerals you put in those places, the conclusion will hold. That is, Hilbert is saying, these are not to be understood as variables that range over numbers. These are to be understood as placeholders whose places would be occupied by numerals. The statements that we make in number theory, these are really statements about numerals. And we're using shorthand for those statements. So Hilbert says, for example, the associative law. Let's see, is there? I mean, just can I read them?
Absolutely,
Yeah.
yes.
The associative law, A plus B equals B plus A. This is to be understood as saying that no matter what numerals I put for these, I will get a correct equation. So this does not have a negation, he tells us. This is not to be understood as a quantified statement, which would have a negation. No, this is to be understood as an instruction for thinking about numbers. And instructions don't have negations. This is telling you that no matter what numerals you use for A and B, adding them in this order would give a true equation with that order. Now, when I say something like his idea of contentual mathematics, I don't believe Hilbert had a very, very clear idea of how to spell this out. If he did have a clear idea, he changed his mind a lot. That's obvious. If he had a clear idea, he changed his mind a lot in successive essays in the 1920s and 30s. But I think he has an important idea. So this is not to be seen as a general statement about numbers. It's to be seen as a statement about generic numbers, whatever numbers you thought these were. Because he's assuming you think there's some numbers. They're not ranging over all numbers. You're thinking that there's some numbers. And whatever numbers you were thinking they were, this would be true. You see this step in generic numerical terms. Every Fermat triple gives an elliptic curve, and it gives a modular curve where n is the product of the primes in ABC. So this is computable. I'm not going to write the definition of the modular curve, but I will go to the trouble of writing the definition of the conductor. It's the product of the primes in those three numbers. So this is a generic computation. If I had given you A, B, and C, you could find their primes and you could multiply them together. You would know what n was. And given n, if you knew enough about modular forms, you would know what modular form defines that curve. So in that sense, it's computational. You do know these things. It gives a dominant map to that curve. Related forms let you lower the number n. This is Ribot's theorem. Down to 2, which you can show is impossible. This is an outline of the proof. This is, I think, a fair depiction of the mathematical content of the proof. The content that people who are familiar with this proof like to think about. Yes, they say, yes, this is what happens. There's an elliptic curve. We know how to give an elliptic curve, we know it's modular, and so we know how to find a modular curve that has to map onto it. We know we could reduce the level, and we know that these levels can't be arbitrarily reducible, so there can't be such a curve. So, I should have mentioned in the Fermat case, the related forms have lower n. It's a crucial step that this is in the Fermat case. If your n came about from something like from a Fermat triple, then you can. Oh no. The point is, if it comes from a Fermat triple, it can't go down to 2, right? It can always be lowered, but if it came from a Fermat triple, it couldn't go to 2, and so this is impossible. There can't be Fermat triples. Hilbert enunciated what he called a new finite inference rule. He said, when we have a formula with a numeral z in it, when we have a formula, we've proven a correct numerical formula for every assigned numeral z, then the generalization can be taken as conclusion. Remember, this is not a generalization. This is a numerical formula for unidentified numbers. But if we know it holds for every pair of unidentified numbers, then we can take this conclusion. Because the whole point here is to keep track of what's concrete mathematics and what's abstract. This is abstract because it quantifies over numbers. This is concrete, even though it's any number of different concrete cases. This is a bunch of concrete cases. This is an abstraction. what holds in every numerical case is general. And I'm thinking, this is what people are saying when a mathematician talks to me. I didn't ask anybody's permission to use their names. But I mean, friendly mathematicians talk to me and they say, well, Colin, I see the numbers in each step. I don't know why you're concerned about where this is proof, because I can see the numbers in each step. And I said, well, that's the kind of argument that Hilbert's talking about. When you can see each step with numerals, then you draw the general conclusion. And the proofs of Fermat's last theorem are seen numerically in every numerical case by the people who follow them, which currently not everybody follows the proofs of Fermat's last theorem. But the people who do tell me, yeah, I mean, I see this, and I believe them. I see this numerically in each case. So Hilbert's, this rule that I had up before is called Hilbert's omega rule. It's a compelling thought. It deserves reflection. I think okay, here I'm talking as a philosopher, If you want to understand what a lot of number theorists are doing, you need to understand the idea of a generic numerical instance that isn't a generalization. There really is something else going on here than just summarizing general rules. But is this an inference rule at all? How is this statement proven correct for every numeral z? How do we know that this holds for all numerals a and b? Is knowing this for all numerals a and b really different from knowing this generalization? So somebody says, I see each step of the Wiles argument or the Kissen argument, but there's lots of arguments now. I see each step. How do you see each step? I want to know. And this is the role of proof. This is what proofs are for. We don't just have a notion that something must hold in every case. We prove it holds in every case. And the point I want to get across to say some of my number theorists is, even if you knew that held in every numerical case, of course this does not prove that does not show it's provable in power arithmetic. Holding in every numerical case is not the same as being provable in power arithmetic. Indeed, it's not the same as being provable in Zermelo-Frankel with choice. PA doesn't cover all concrete numerical truths. Nor does Zermelo-Frankel with choice cover all concrete numerical truths. This is Gödel's completeness theorem. We know they don't. Knowing that it holds, even if you could somehow know that this holds for all concrete cases, we know that power arithmetic doesn't only describe the concrete cases. We know that Zermelo-Frankel doesn't only describe the concrete cases. If you want to look at a model theoretically, these things have non-standard models. To know that it follows in power arithmetic is not to know that it's true in every concrete case. It's to know that it's true in all the cases, including non-standard cases that model PA. To know that it's provable in Zermelo-Frankel is to know that it's true in the standard model and also all the non-standard models admitted by ZFC, which are much narrower than the ones admitted by PA. But they're still there. Knowing this holds for all concrete cases isn't knowing that it's provable from one set of axioms or another. In a sense, it's the opposite of knowing it's provable from some axioms, because we know that none of the axiom systems is complete. We know that FLT is provable in ZFC because the proof's been given. Of course, the proofs as published aren't literally in ZFC, but it's no problem. You see how to. As I've said in some journal articles, if you follow the references in the proofs, they use Grothendieck universes, but no problem eliminating Grothendieck universes in favor of just Zermelo-Frankel. So we know it's provable. We know ZFC proves this because we can give the proof. We know PA proves this because we can give the proof. That's different from knowing it holds in all concrete cases. And all the more is it different in the case of Fermat's last theorem. We know that Fermat's last theorem is provable in finite order arithmetic. Simple theory of types with infinity. So this is like nth order arithmetic for all finite n. We know it's provable there because it's been done. I can show you it's provable there. And I can do better than that. I can show you how to translate any of the published proofs, including all the parts with Grothendieck universes, into a theory that's conservative over finite order arithmetic. You need numbers, sets of numbers, sets of numbers. You need this for every finite level, and then you need some classes to form your toposes, your derived categories. You need some classes, but only a very weak theory of those classes. Essentially, you don't need comprehension principles for those classes. You just need inference rules for them. As I say, I've been working on how to prove Fermat's last theorem with as little comprehension as possible. It's not theoretic comprehension principles. And we know that can be done because I can show you it can be done. I absolutely share the confidence that Fermat's last theorem can be proved in parallel arithmetic. I don't expect there's any problem in principle. Current proofs are very far from being stated in parallel arithmetic. I don't expect that there's really a problem in principle proving it in parallel arithmetic. But this is not yet known the way other results in proof theory are known. When you look at Kreisel's arguments to show that various statements of analytic number theory can actually be proved in PA, they're detailed arguments. He gives arguments. He shows you step by step. We don't have that for Fermat's last theorem right now. We have a confidence that it could be done, but we don't have the kind of proofs that are typically given to show something's provable in parallel arithmetic. There's just a lot remaining to be done there. Now, parallel arithmetic is a natural pivotal theoretical reference. It's natural to ask, can this be proved in parallel arithmetic? There's a lot of reasons for that. Parallel arithmetic gives you a lot of elbow room, but it's clearly about numbers. It's a natural question to ask, but you know, as logicians, parallel arithmetic cannot be the weakest arithmetic adequate to the theorem. Parallel arithmetic isn't the weakest arithmetic adequate to any theorem. Just by compactness and reflexivity. Parallel arithmetic proves consistency of all its finite fragments. Any one proof in parallel arithmetic only uses finitely many axioms. So any proof given in PA can already be given in some weaker theory whose consistency is provable in PA. By that standard of weaker theory, a theory whose consistency is provable. We know that parallel, and I think it's at least of some theoretical interest to see, we know now that if FLT can be proved in PA, it's proved in some weaker theory. It's likely that if it's proved in PA, it's proved in some identifiable, interesting weaker theory. And it would be interesting then to identify that weaker theory. There is a candidate for that I'll come to. But more pointedly, I want to argue that parallel arithmetic cannot explain the expert feeling that the proofs are concretely arithmetic. That can't be what's going on when people say, look, the substance of the proof is already in arithmetic. That can't mean it's in Peano arithmetic. Peano arithmetic is not a very concrete theory. It's not finite in Hilbert's sense. And I think Hilbert actually gives a good explanation of this. I could put it more in principle and say, look, Peano arithmetic, allowing induction on arbitrarily high quantifier complexity formulas, is not close to what we ordinarily mean by arithmetic. It's not bounded to be close to what we ordinarily mean. You can define some very weird stuff in Peano arithmetic. But I want to look at Hilbert's explanation of this. Hilbert has an interesting claim. To say that every number n is less than some prime, he tells us, this is not a concrete finite claim. Why is it not? Because the concrete claim would be every number n is less than some prime less than n factorial plus 1. If you haven't told me how far to look, you have not made a finite claim. Now, of course, Hilbert gives this example because he knows we're entitled to put that bound on it. But he says if you haven't put the bound on, then you have not made a finite claim. And I think this is close to what's going on when a lot of people say, well, look, this proof really is it's just arithmetic. They mean it's not just that the steps are calculations which would somehow end in any concrete case. It's not just that you figure it could be done somehow. One already knew that for the prime number theorem. In any given concrete case, if I want to know the density of primes below a given number, I could just crank through and find that density up to that number. That didn't make people feel it was concretely arithmetic because you didn't know how long it would take. You couldn't foresee what these calculations would look like. But in this case, and I think typically in cohomological number theory, you see how each calculation is concretely bounded. It's some calculation on a 12-dimensional space over the integers mod 5. You know how it's going to go. I mean, you don't know in detail how it's going to go, and it may be the number of well, it won't always be mod 5, right? It could in principle be mod any prime. But you actually see the bounding, I think. This is my conjecture that as we explore this, we'll verify that you can really see the concrete bounds. Because when I'm talking with a number theorist and they say, look, this really is arithmetic, I'm determined to explain that. I'm not determined to argue whether it's true or not. I'm determined to take it as true and explain what it means. And I think this is, and I want to argue without vast experience of this, that this is typical of cohomological number theory. As weird as cohomological number theory looks to a lot of people, which obviously not the people who are comfortable using it, but I can promise you lots of mathematicians think it looks weird. It's in an inexplicable way very directly arithmetic. Because these calculations, you can always see how these calculations are bounded. And that they can be uniformly verified. This is the question. We see how to sort of verify this no matter what numerals you take for A and B, the verification here is going to be pretty much the same as for any others. There's not going to be any surprises in how you verify this. In that sense, the verification will be uniform. So you're entitled to say this really is a concrete claim. By Hilbert standards, of course, this is not, because it doesn't tell you how far you might be looking. I would hope to, in this way, elucidate cohomology as an organizing device. Cohomology is not a weird machine that comes in and changes stuff so that then some people can get theorems. It's an organizing device. It's an organizing device that, it's organizing material that you're used to. So that's my project is to get all of this done. In terms of, as you know, we're having this meeting in Warwick at the end of next week on prospects for getting the meat of Fermat's last theorem into Peano arithmetic, maybe explicitly. I mean, not that we're planning to do it, but to show it could maybe figure out how it could be done specifically, more likely show proof theoretically that it could be done, but in an articulate way where we really have shown it can be done. And that's going to be looking at a lot of work in Galois theory in the statement of modularity, just winding it down, getting it into Peano arithmetic. The work I've already done on this is about Grothendieck universes. I mentioned, okay, what is a Grothendieck universe? A Grothendieck universe is the universe of sets of rank less than some strong inaccessible cardinal. These are very large sets. These are sets so large that Zermelo-Frankel doesn't prove they exist because they model Zermelo-Frankel. I mean, that's the naive description of what is a universe. A universe is a set which models the Zermelo-Frankel axioms in the most natural way. It doesn't just model them somehow. It models them where what appears as the power set really is the power set. That's a great deal to ask. Zermelo-Frankel already won't prove that any set models Zermelo-Frankel at all. let alone that it models it in this natural way, where transitively with actual power sets. That's what is a Grothendieck universe. What I can show you is that you don't need sets that big. You can go to the SGA, we talk about universes a lot, and you can rewrite the appendix where they introduce the concept universe. Basically, you drop the replacement axiom scheme from your set theory. And you don't even just drop it in favor of separation, you drop it in favor of bounded separation. Bounded separation is a very much weaker principle. We're now in, as a matter of fact, Lauvier's elementary theory of the category of sets, which is how I first saw it. Or you could say it's simple theory of types with infinity. It's the same way, same string. I want to give Grothendieck credit here in a way that I think should interest logicians. Grothendieck cared to give a fully rigorous foundation for what he did. Grothendieck says, look, I know I'm throwing around a lot of large collections, and Sarah is saying I don't need to do that, but I want to do that. And other people are saying, how do you know you're allowed to do that by your set theory? Oh, if I suppose there's a universe, that's easy. Grothendieck and Dieudonné were both going over Bourbaki notes on set theory, the notes preparatory to the book. So you knew about Tarski's idea of strong inaccessible cardinals. Grothendieck doesn't invent the idea of Grothendieck universe. He takes it from the set theorist, but he says, oh, that's so big, I can easily use this. He cares to give a rigorous foundation. What he doesn't care to do is worry about finding the weakest one. This is of no importance to him at all. I heard a nice conversation between Pierre Cartier and Jean Benamou about Grothendieck, where they were agreeing that Grothendieck didn't really believe in universes. What he believed in was toposes and schemes. That is, the set theory is only there so that you have something there. It's not the point at all. The point was that you should have this very nicely unified theory of toposes. And why do schemes use large? Because schemes are representable functors on categories of rings. So now when you look at it in that way, there's a set theoretic problem. How big a category of rings is this? Can we really talk about set value functions on it? And Grothendieck says, well, sure, you can with universes. For Grothendieck, a scheme was always a functor on a category of rings. Maybe be representable in some categories and not others, but they're always set value functors on rings. And I think we should give him credit for wanting to get that right. He's got two reasons not to look for the weakest theory of universes. One is that he doesn't care. He doesn't want to work that hard. The other is he does not really know in 1967 or 1973 what all constructions he will need to justify. He doesn't know whether he's going to need replacement at some point or not. He has used replacement to prove existence of sufficient injectives. It's a technical lemma at the base of derived functor cohomology, where he has used the axiom scheme of replacement. He said, I've got this module, I want to embed it in a module that's really nicely ripped apart, so that then I can look at how to rip it apart. And to do this, I know how to do it step by step, but now I want to repeat this step as many times as needed. It becomes a transfinite induction, and it becomes a transfinite induction of arbitrary length. So that's axiom scheme of replacement. And he doesn't care whether he needed to do it that way or not. Well, okay, for some of us who are logicians, maybe we take the time to care, and we'll find he doesn't need to do it. So he posits these very large universes. We don't really need them that large. But a Grothendieck universe does have a plain explicit meaning, so you can actually prove that you could not do without them. How I can eliminate universes is take nth order arithmetic for all n, and then just add this layer of classes over it with no comprehension principles. I did want to contrast this to something that logicians hear a lot about lately, universes in various type theories. A homotopy type theory, various type theories. They'll talk about universes. And you'll hear people say, oh, this might use a Grothendieck universe or maybe two Grothendieck universes. But it's a question of what are your type constructors. These type theories never have replacement in them. A universe is a type, sure, you can say it's a type of all types. What has to be in a type of all types? That depends how you're allowed to construct types. If your only type constructors was that any two types have a product, you don't need Grothendieck universes to have a type of all types. Even if you were also allowed to construct power types, doesn't take a Grothendieck universe if you don't have something like the axiom scheme of replacement. There's a lot of loose talk about universes. I'm in favor of having those a lot of the time. But then when people say, oh, I might need one or two Grothendieck universes here, no, typically they're nowhere in the ballpark of the strength of Grothendieck universes. Grothendieck was in that ballpark. One of the theorems he has to justify, so far as he knew, used replacement in his proof. Yeah, but as logicians we can find it didn't need replacement. As logicians, I think we might expect it didn't need replacement. Commonly, when people think they're using replacement, it's not really needed. It's hard to find theorems of set theory that need replacement. They're found, but it's harder than just seeing that the first published proof used it. So replacement. And I see this as an exercise in trying to develop Grothendieck's perspective. It's not that Grothendieck cares about the set theory. It's not that I'm suggesting most people care about the set theory. Grothendieck does care about the unification that he can get by having enough sets to say there, after all, is a topos of sheaves on any site. There, after all, is a set of geometric morphisms from this topos to that topos. We want to be able to do this, and we can. We can do it with nothing like the strength of Grothendieck universes. Grothendieck's perspective, I think, as a biographical matter of fact, is not much about arithmetic. Grothendieck knows he's solving problems in number theory, but he does not think number theoretically. I mean, when you read Récolte et Sommeil, he goes to Serre for that. He says, Serre, what would you need to prove here? And Serre says, oh, you need to prove this. Okay, I'll find a way to do that. Grothendieck is not interested in bringing things down to arithmetic. But what he is interested in is having unified tools. He calls these houses ready to live in. Tools that people can use without worrying about them. They're there, they're correct, they're provably correct, they're usable without worrying about them. So that somebody wants to give a proof of Fermat's last theorem, can do what the published proofs of Fermat's last theorem in fact do, which is refer out for the proofs of some theorems, of the algebrogeometric theorems that go back to EGA or SGA. You refer out for those. And interestingly, Grothendieck himself refers out for the proof of sufficiency of injectives, the used replacement. That proof does not occur in SGA. It's cited to his Tohoku paper. We need to do that. There are books that say in the preface, we won't use the word topos. There's not a lot of words in math where people put in the preface that they're not going to use it. This is an unnecessary anxiety. Don't fear the word topos. Use it if you want to use it. If it doesn't come up, it won't come up. But don't be afraid of it. And I think a lot of the reason people don't want to get into set theory. They don't want to get into large cardinals. And in fact, you don't need to. However, this is the cohomological apparatus. It's not the topic of the sessions next week in Warwick. This is up above that. Next week at Warwick is down in the more arithmetic manipulations, which are sort of visibly third order arithmetic. It would be nice to know their Fermat arithmetic. That's a different issue, though, and not one that Grothendieck is much interested in. It's one that Barry Mazur, for example, is interested in, not Grothendieck. Okay, well, that's
Okay, thank you. do you think that Grothendieck style mathematics would come under Hilbert's notion of contentual?
It's interesting because for Hilbert, I thought about this morning and I didn't come up with anything particular to say. For Hilbert, the contrast he makes to contentual mathematics, the one he emphasizes, is ideal elements. We add points at infinity to geometry, as opposed to just a contentual geometry. In Hilbert's formalism, and his most formalist, he never says mathematics is all about finite numbers. He says it's about finite numbers and sufficient geometry to recognize the numerals. There's always geometry in there too. But this is geometry of finite points. Now, from a certain point of view, I want to say it's not just points at infinity that are hard to picture. Points a million miles from here are hard to picture too. But his contrast is contentual mathematics versus ideal elements. He complains about people who don't think that complex numbers exist. He says, but we know how to use them, it doesn't matter. They're ideal elements, but we know how to use them. That's what he talks about, and yet his examples are about higher order organization. What's going on here is all higher order organization. It's not ideal elements in particular, but commonly we pass from the integers to the integers modulo some prime. In that sense, it's not that we add, integers at infinity or something, but what we do is we have very high levels of organization of this. We take a module of integers, we take the category of modules, we take the category of categories of modules, we take the category of functors categories on the category of categories of modules. Hilbert never imagined anything like that. I think an important perspective to keep in mind on Hilbert is the one that Leo Corey develops. Hilbert does axiomatic algebra, but he doesn't do abstract algebra. Hilbert's axiomatics always have natural models. You can see what the intended models are. But Hilbert does take care to promote the career of Emmy Noether. And Emmy Noether does abstract algebra because she has learned that very weird organizations with no immediately plausible intuitive meaning can solve important problems. But that's Noether, not Hilbert. And that perspective, that's a perspective we see triumphant in Grothendieck. All kinds of organization are worth doing. They will yield results. Hilbert's not so close to that.
Sorry if I missed it. Did you say what system you thought, what subsystem of PA would be usable for?
Right, I didn't, and there's a slide that elementary function arithmetic or exponential function arithmetic, Harvey-Friedman's grand conjecture. It is Harvey-Friedman, what is exponential function arithmetic? It's arithmetic where the quantifiers are all bounded and they're bounded by iterated exponential functions. Here's an iterated exponential function, even if squaring wasn't a function, even if you see it as a case of the exponential. This is, I think, a very concrete kind of arithmetic in Hilbert's sense. Now, I do not really want to continue some process 2 to the 2 to the twice n plus 1 times for any very large n. But still, in principle, it's a calculable bound. It's, I think, a concrete bound. Iterated exponentials are vastly more concrete than primitive recursive functions in general, let alone recursive functions in general. So I'm attracted to it from that point of view. Harvey has conjectured that Fermat's last theorem is provable in exponential function arithmetic, elements, same thing. He's conjectured that every theorem ever proved in the annals of mathematics that doesn't explicitly deal with large sets is in fact provable in elementary function arithmetic.
Ramsey's theorems. Ramsey's theorems.
Well, okay, but close. But is Ramsey's theorem proved in the annals of mathematics? What I think is great about this conjecture is that apart from some examples like this, it's surprisingly unrefuted. What we don't see is things that, oh heck, you really needed a little more than that. I mean, we've got Ramsey being a lot more
The
than
finite version of Ramsey's
Yeah,
theorem.
the final,
Yeah.
yeah. But there we need a function that's not even provably recursive in PA.
No, the ordinary version of
Oh.
Ramsey's theorem. The finite version of Ramsey's
Oh,
theorem
just-
needs iterated exponentiation.
Oh, okay. Oh, well, this, we have expected.
No, not iterated.
Hmm?
For Ramsey's theorem for n tuples needs the 2 to the 2 to the 2 n times.
Yeah.
So
The
to prove it
the
for all
tetration.
n, you need iterated exponentiation, which is not a provably total function.
Well, I would not call this iterated exponentiation. I would call that tetration or variably iterated exponentiation. An iterated
It's the next thing in the acronym.
Yeah,
hierarchy,
an iterated exponential is some iteration of the exponential function. Is that the terminology I would use? But yeah.
Yeah, but that will only prove Ramsey's theorem for
Yep.
triples. You need, to prove it for all n tuples for all n, you need n iterates of exponentiation.
Okay, the versions of the discussion that I've seen, that's the kind of Ramsey's theorem that includes that the set has to be larger than its smallest element.
No, that's the
No,
Paris
You don't need
Harrington
that.
statement.
Okay, you don't need it for the.
No,
Oh,
that's
I see
not
what you're
even
saying.
proved.
Oh, okay,
with
so you're not
contentual
talking independent of PA, you're just
No,
talking.
no.
But
This is
independent of
proved
EFA.
in
Yeah,
PRA,
okay,
but
yeah.
it's not proved.
But not
in
the EFA, yeah. But with just sort of isolable exceptions like that. Hardy's conjecture is pretty good. I mean,
No, well,
It's pretty complicated.
I mean,
Mhm.
if it's a pi 0 1 statement, then it's a reasonable conjecture, but not a pi 0 2 statement. That's-
because of course, reverse mathematics is full of statements that are stronger than EFA. But Hardy's
but
claim
that's
is that
second
those
order
statements don't, well, no, but they're second order theories that are conservative over first order theories that are stronger than EFA. First order fragments of counter arithmetic stronger than EFA. But Harvey wants to say, those statements don't actually occur in the annals of mathematics. They're generalizations of statements. Well, but, and for a serious reason. The statements that occur in the annals of mathematics are special cases, are identifiable, and in fact identified special cases. What's,
You mean the journal?
yeah. Yeah. So I'm not concerned to argue his thesis, but well, I mean, you may be right against me when I said it's surprisingly unrefuted. Maybe it's not so. Maybe it's perfectly adequately refuted. But in terms of this context, what Harvey says about EFA that I think is exactly right. This is the weakest natural fragment of Pound arithmetic in which tupling has the desired properties, in which you can code n tuples and get a standard theory of n tuples. Yeah, with n as an arg varying uniformly. Yeah. I'm interested in pursuing the claim that this can be proved in exponential. I'm not committed to the claim it can be done, and I'm certainly not committed to saying I can show it can be done. But I'm interested in pursuing whether it can be done there. Yes.
We don't know what the elective mean. But if the claim is that any statement of that Hilbert type of there can be turned into a concrete statement of the document of this display type, then I find very hard to believe. I mean, we refer to the top homology, but for example, the torsion inside the second and top homology of an algebraic surface, I don't know any algorithm going to compute that.
Yeah, well, now that's a really substantial objection. That would be to say that there might be steps of this that really resist being done in Pound arithmetic. What I would say about a lot of them, I mean, what you see on the face, I'm interested in, so let's say, fragments of nth order arithmetic that are conservative over some fragment of Peano arithmetic. And I'm happy to work in this nth order, second order, third order, fourth order, as long as I know it to be conservative over this. I don't really expect to display proofs in Peano arithmetic. I would like to be able to show that every step there can be displayed in a fragment of nth order arithmetic that's conservative over Peano, or even conservative over elementary function arithmetic.
and so on. I mean, Roth's theorem, even Tui's theorem on Diophantine
Yeah.
approximation.
Yeah.
I mean, they rely on taking one good approximation and proving there's at most two
Yeah.
more or something like that.
Most of those things are ineffective.
And they're
Yeah.
completely
But that's where we're getting into substantial statements that I hope will be true, that for very good reasons, those don't occur in most arguments in cohomological number theory. Arguments in cohomological number theory are about Galois theory of finite modules over finite fields. And those things aren't going to occur. That's a substantial claim. It's not obviously true, but I think it's likely to be true.
So the proof doesn't use any general finiteness theorems?
It uses lots of
Which
finiteness
are
theorems,
not
but I
finite.
hope that none of them are deep. It uses, in fact, very many finiteness assertions. But the hope is that none of them are deep, that none of them are Roth's theorem. Or, you know,
just Siegel's theorem, no integer points on curves of genus. I mean, that.
so how is it, curves of genus n don't occur in the proofs of Fermat's
Genus
theorem.
one.
Genus 1 does.
Yeah, but there's only finite many integer points on those, and that proof is, as far as I know.
No, many curves of higher genus and higher dimensional varieties occur in the proof.
Yeah,
It's just
yeah.
hidden.
Well, yeah, that's the question, how did, and what's needed about them.
I mean, all these color representations
Mhm.
that whose converse classes you're using are all constructed using higher dimensional varieties.
Yeah. Well, like you say, my direction here is coming from talking to a lot of number theorists who tell me that they can see it all as arithmetic. Now, they may be over-optimistic. Perhaps they can't see it all as arithmetic in that sense. But I think it's worth exploring. I think it's worth trying to say these things articulately and clearly so we can tell. Yeah, and if it comes down to, yes, when I articulate this step in Ribot's theorem, I really do need Siegel's theorem. Because Siegel's one of the ones that's not currently effective.
Yeah.
If you can show I really do need that, I would be surprised if Ribot's theorem depends on those cases of it. But I think it does. I mean, it certainly cites Siegel. I mean, it's, you know. And if that happens, then I'll go back to some of my number theorist friends and say, well, you did underestimate this. Yeah, I am not committed to what the outcome will be here. I've got some ideas that I want to pursue, and I've got some ideas of what I think might be expected as an outcome, but I'm not committed to saying that will be the outcome. Yeah. These are huge proofs. Fermat's last theorem, as the proofs get simpler and simpler, more and more general, more and more streamlined, they remain huge. There's a lot going on here. And I want to say Fermat's last theorem is a huge event too. There's a long tradition of mathematicians saying, well, after all, it's not that important. The reason there's a long tradition is it is that important. That's why people keep saying it's not. This is a subject that deserves logicians' attention. There's a lot here, and we don't know what we'll find as we go into it.
Could I just ask, isn't there a system that one can say, I mean, very simply, that if Fermat's theorem is provable in PA, then it's provable in this very considerably weaker system, namely, I think, something like sigma 1 induction is enough. Because all you have to do, you take Hilbert's actual proof that he gives in terms of Fermat's theorem, sketchable proof in the 1927 paper, in which he shows that if you have a finitary consistency proof of a finitary consistency proof of a theory, then it can be used to give and you have an infinitary proof of Fermat's theorem, e.g. in gamma arithmetic, then you can give a proof in a finitary system. Now, that, of course, he was wrong that you could have a finitary proof, but you could have a consistency proof using sigma 1 induction, and that would be enough to give you, by that very argument, a proof of Fermat's theorem in this very considerably weaker system than PA.
Once it's a PA proof.
Yes.
Yeah, once you know it's a
But I
PA
know
proof
that's
at
what
all.
we're talking about. I mean, you were saying, your point was, the issue is it provable in PA? But then, once you get it provable in PA, then it's going to be provable in something a lot weaker than PA.
Well, that's That's true in principle, that's provable.
Yes,
What's
but-
not provable that way is that there'll be any interesting weaker theory. But your argument might show that there has to be at least this interesting weaker theory.
Yeah, I mean, I think
Yeah.
that's clear.
As I said, getting into PA is a really vital theoretical pivot point.
Sure, sure.
Even
But
though
I'm
it
saying
can't
that
be
once
the
you get
final.
it there, then you
Yeah.
immediately know that it's in a much,
Yeah.
much weaker
Yeah.
theory, and you can identify exactly what that
Yeah.
theory is.
And I expect it's in PA, but I would really like to, I would myself like to know more about how can we show it's in PA?